Hi, I'm Ryan Self, and my talk today is on online observer-based inverse reinforcement learning. And I did this work with fellow lab mate Kevin Coleman and advisors Dr. Bai and Dr. K at Oklahoma State University. Here's the outline to my talk. I'll go over introduction, including problem and motivation and problem formulation. I'll then go over the inverse reinforcement learning formulation. I'll show our observer-based IRL methods, and then I'll go over simulation example. IRL is based on the premise that the most succinct representation of behavior entities is word function, and IRL is trying to aim to uncover this word function. Inverse reinforcement learning is a subfield of learning from demonstration that's been highly successful in a variety of situations, such as socially aware robotics and helicopter robotics. It could also be used for path recommendation platform, where you get reward functions describing human operators and use that reward function to then generate paths for them to recommend them to follow. But why are we focused on online IRL? Well, most IRL methods have been offline. However, online IRL methods would facilitate better adaptability to changes in system dynamics, your environment, or your overall task objective. It could also be used for intent monitoring. If you have a known reward function agent is supposed to act with respect to, you compare that to your estimate online to see if it's misbehaving. It also could be used in closed loop formulation with reinforcement learning to get an online learning and control situation. There are many challenges to online IRL. We've detailed out 5 here, including non-uniqueness of solutions, partial measurements, inconsistent behavior, and sparse and limited data. But the focus of today will be imperfect and noisy measurements. So the objective is to develop online IRL methods to utilize a single demonstration of noisy data. And this work focuses or builds on previous work that we have for both linear and nonlinear systems. Let's get into the problem formulation. So we have an agent under observation. It has some set of linear dynamics. The agent is attempting to minimize an LQR cost functional, where we're trying to estimate Q and R by using noisy measurements of X and U. Since the problem is LQR, we know the exact basis functions for both R and Q, so they can be parameterized, shown here, such as U transpose RU with ideal weights to be estimated, known features, and similarly for state deviation penalty. Since this is an LQR cost functional, we know that Q and R are both going to be symmetric, so without loss of generality, we're going to be estimating the main elements that go down the main diagonals and elements that fall above the diagonals. Now let's get into the inverse reinforcement learning formulation. So if X and U are optimal, we know that they satisfy the Hamilton-Jacobi-Bellman equation, but more specifically, the HJB equation is equal to 0 for all time. In addition to that, we know the form of the optimal feedback controller shown here. However, there's one piece of information that show up in here that's optimal feedback or optimal value function. So we can parameterize that, such as X transpose PX, where we get ideal weights to be estimated and known features. And in this situation, these features are identically equal to the features and the state deviation penalty of the reward function. If we use all of our estimates for the reward and optimal value function weights into the HJB equation, we get our first error metric that we formulate what we call the inverse Bellman error, where this is our error term shown here, and this is the parameterized estimate or parameterized form of the HJB equation. From the optimal controller, we can parameterize, if you multiply R on the side over here, you can parameterize RU as ideal weights and known features and ideal weights to be estimated. If you use estimates for R and the reward function and optimal value function in the optimal controller equation, we get our second error metric, which we call the control residual error, where this is the error term shown here, and this is the parameterized estimate of the feedback controller. Now, if we augment these two error equations into one matrix formulation, we get this augmented error term shown here, where this is the inverse Bellman error and the control residual error, and then the corresponding features. And these are all the weights we're going to be trying to estimate in this formulation. If X and U are optimal and the weights are ideal, then the inverse Bellman error and the control residual error will be equal to 0. So this is essentially turns into a minimization problem. However, this minimization problem is ill-posed. If we look more if we look more specifically, if you set all these weights identically equal to 0, this trivially minimizes this problem. However, since this is LQR problem, R must be positive definite, so this is not a useful solution. Also, in optimal control theory, we know that a reward function, a positive scaled multiple of that reward function utilize the same trajectory. So how can we differentiate between these reward functions if we're just monitoring trajectories online? So one way to combat these two issues is that we select one weight to be known. So we select the first element of the R matrix and we pull the corresponding features out of error the error matrix to get the updated error matrix shown here. Now let's get into the observer-based IRL methods. Our observer problem, we're going to be augmenting the system states and the weights to be estimated online, and we get the augmented state dynamics shown here. Since the weights are going to be constants, the dynamics will be 0. The output for this observer will be combination of our measurable system states and the single weight that we pulled out to be known, and then we can get the general formulation of the observer shown here, where K is the gain matrix to be designed. Let's get into the memoryless observer. So the first observer we're designing is a memoryless observer, so it's just taking the current measurement and formulating an observer to estimate both the state and the unknown weights. So this is the general formulation where this is our measurement vector and our measurement model. And we're going to be designing K in order to estimate these online. So this is going to be a block diagonal matrix. We're designing K1 and K2. This leads to our first theorem. So the K1 is selected that A minus K1C is Hurwitz, and K2 is selected to be symmetric positive definite. And G is persistently exciting, then we know that the error converges to 0 as the limit of T goes to infinity. Even though the system is linear, this is a nonlinear observer because the features of the observer are nonlinear. So we can't use common techniques to ensure PE, such as counting input frequencies. Sometimes nonlinear PE monitoring it online is difficult. So this is the main motivation where we develop our history stack observer. So the history stack observer will be similar to the memoryless observer. However, we'll be developing the measurement and the measurement model. Instead of at the current time instance, we'll be storing them from previous time instances as well. So we'll be stacking the measurements and the measurement model at different time instances T1 through Tn into these matrix forms, where this is our measurement and our measurement model at T1 all the way through Tn. This leads to another gain matrix for the history stack observer that's going to be block diagonal. We'll be designing K3 and K4 in order to estimate these weights online. So this leads into another theorem. Before we get to that, we need some definitions. We call history stack full rank if it satisfies this equation. A signal is finitely informative if there exists some time instances, such as history stack's full rank at least once, and persistently informative if the history stack can be replenished as many times as we need to for all t greater than or equal to 0. So this leads to another theorem, such that if all these are true, the error signal is bounded if the signal is finitely informative, and similarly to the memoryless observer, it converges to 0 if it's persistently informative. The ultimate boundedness is the main distinct advantage of the history stack observer over memoryless observer, where if we lose persistently exciting signals, the history stack observer remains bounded. However, there is no such guarantee for the memoryless observer. Now let's get into a simulation example. So the first one will be a noise-free environment. So we have an agent under observation has linear dynamics shown there. We're going to be trying to estimate the LQR problem where Q is a diagonal of 2, 1, and we have a single controller. In order to ensure persistently exciting signals, the controller that the agent is implementing is the optimal feedback controller plus an exciting signal added to it. And this will be the error metric used in our graphs. So here's the first noise-free environment graph. This is basically just to show that the memoryless observer and the history stack observer are working perfectly to align with what our theory tells us, is that all these errors should converge to 0. So we have 3 variations of the history stack observer and the memoryless observer. Now let's go into the noisy environment. We did simulations over 3 different noise variations, so no noise, low noise, medium noise, and high noise. We did those over 50 simulations, and we averaged the trajectories overall for 50 simulations. So concurrent CL stands for concurrent learning. So this is just our standard method that we're not doing any we're not doing it's not the observer filter method. And then we have 2 variations of a history stack observer, so an exponentially changing gain matrix, and a Kalman filter implementation of a history stack observer. The most important line to be looking at is the bottom line shown here. So as you can see, the errors for both the exponential HSO and the Kalman filter HSO are significantly smaller than the standard concurrent learning inverse reinforcement learning method for the highest noise simulation. This is a graphical representation showing the exact same information for the high noise situation. So this is the standard deviation of 1. The left is the concurrent learning method, so there's just the standard IRL method, and the one on the right is the observer formulation for the history stack observer. And as you can see, the errors are significantly less in this noisy situation for the history stack observer compared to the standard concurrent learning IRL method. This research was supported by NSF award, and I want to thank you for your time, and we're happy to take any questions that you all may have. Thank you.